All right, awesome. This is a presentation on LoRA, also called low-rank adaptation of large language models. So just to briefly start like an introduction motivation for this. Applications in NLP rely on adapting large language models to multiple downstream tasks. For example, to doing like generation of summarization. You could have graphic text generation and so on. And for even natural language understanding, you have like sentiment analysis as well. So, and this adaptation can be done in a few different ways. One is you can take the entire model and fine tune it, which works really well if you have a small model, but it's extremely painful and annoying if you have a bigger model like GPT-3, for example. The other way is that you can essentially tune some input prompts. I'm probably going to butcher the description of this, but essentially, you can think of it as like you're training a set of a word embedding model for special prompt tokens, and then using those prompt tokens to condition your inputs in your pre-trained model. If anyone knows what like prefix tuning is, please do interrupt, because I wasn't very I was having some difficulty trying to understand that. Then the problem with this is that these pre-trained models also are bound by a sequence length. Like for example, if you have a 512 token sequence length, any additional prompt tokens you provide or prompt you provide has to be constrained in that input sequence or that sequence length. So if you have 512 and you have 12, you require 12 tokens for prompt, then you have a remaining 500 tokens for any downstream task you want to perform. Then finally, you can train these things called adapters. Adapters are you can think them essentially as like small models that can be inserted into a pre-trained model. So for example, if you have a transformer, you can add the adapters into these transformer layers, and I'll provide actually a picture of the last two here, the prompt tuning and the adapter training the adapters, the adapter layer in the next two slides. And the problem that with these adapters is that they can introduce inference latency. So to address these problems, the authors took some inspiration from two prior works, where they showed that over-parameterized models can reside in a low-ranked intrinsic dimension. And essentially, the way kind of understood intrinsic dimension is that it's a dimension in which solutions first start to appear. So if you have a model, a d-dimensional model, maybe let's say it's these are 1,000. If you were to look from 0 to 1,000, there's some number of dimensions. There's some dimension size where you actually start seeing solutions to problems, and that's, if I understand correctly, that's what intrinsic dimension is. It's when like if you have 1,000 parameters, but you see solutions in the first after the first 10 dimensions, and your intrinsic dimension is 10. So what they do. Solutions being like you don't I'm not exactly sure what they meant by solutions, but I think if my understanding is correct, it's when your whatever performance metric you're looking at actually has a non-zero value. That's my understanding of it, but I could be wrong there.
Oh, so is it kind of like the performance on task X is the same on the smaller one versus the full model?
Yeah. So the first the first citation there is what actually where they describe the concept of intrinsic dimension. Let me just double check that. I could probably look at the original paper. It is, yeah, it looks like performance. So when the performance becomes non-zero, that's when you start to see. That's when they've kind of they define as this is when you start to see solutions. So does anyone have other questions?
Wait, what do you mean by performance is non-zero? As in it can do something, or like
It can. I think it can do something.
okay, but can't anything do something? Even like a I don't know, 2-layer neural net can predict next words, kind of. Like this is kind of important, right? To figure out how when you have a good low rank representation, like what exactly is the threshold of deciding it's a good decomposition?
I am not sure.
Okay.
Again, this is not from the, like, they didn't describe this in this paper. It's mostly from a prior paper I'm looking at.
Got it. Okay.
So like from what I see, it's if the performance metric once you're finished training, if your performance metric I think is above zero, then that's when you start to see solutions. That's what they define as seeing the solution.
Okay.
Yeah. So the idea here is that with LoRA, essentially you're taking that that idea of the low intrinsic dimension, and what you're doing is that you have your fine-tuned weights and your pre-trained weights, and if you take the difference of those, you have this delta. What they're doing is they're optimizing a decomposition of that delta, that difference. And I'll provide a figure in the next slide. But essentially, the idea is that the large language model can be frozen and kept static, not touched, and you can train only this rank decomposition matrices. So here's the diagram of LoRA on the right here. So you have your pre-trained weights, and then you have these two matrices A and B. And then R here is that low dimension that they're essentially R is that low dimension, and essentially the advantages of this is that, again, the pre-trained models can be frozen. The pre-trained weights can be frozen, and essentially the only thing you have to do is train A and B. And again, A and B are really small, so if you have what you can do is you can train a bunch of them. You can train a bunch of them for different tasks. And if you want to swap tasks, all you have to do is swap A and B out, and you don't have to touch any of the pre-trained weights there. The other benefit here is that there's a lower hardware barrier of entry, and according to the authors, there's about a 3x reduction when using adaptive optimizers, because you don't have to keep any gradients or optimizer states for the pre-trained weights. You only have to keep them for A and B. And the third kind of advantage here again is that there's no inference latency. And finally, there's LoRA can actually be combined with other prior methods. So like it can be used with adapters. It can also be used with prefix tuning because again, it doesn't directly conflict, or it's orthogonal to those methods. And for this paper, The models are restricted to transformer models, so things like GPT-2, GPT-3, and so on. Does anyone have any questions before I go on? Cool.
Hold on.
Yep.
So I think the diagram show it's trying to transform a d dimension, which is maybe high dimension vector, into a smaller dimension, from d to r, and then transform back from r to d dimension, and then add together. So, and I bet they're training the smaller matrix with the r dimension. That's the training parameter. It's much smaller than the d. By the way, it's d squared and r squared or whatever. So the thing is, the transformation from d dimension to r dimension, I guess it's a matrix also. Is that a matrix?
Yeah. So A and B are matrices. So essentially, I'll go over this in the next few slides, but it goes from essentially D to R. Does a transformation from D to R dimensions, and B does from R to D dimensions, and R essentially can be very, very small. I think in the paper they were able to go up to like R equals 1. So essentially, A and B can become essentially vectors.
Yeah, but my I did not read the paper fully, but whatever transforming D to R, it's a matrix or whatever, or what, or maybe it's a vector. It's a vector, maybe, I don't know. It's a matrix. It's a matrix.
From D to R, meaning, are you looking at A here? That's
yeah.
A is a matrix. A is a matrix from dimension D by R.
Yeah, it's a D by R. Is that trainable parameter? I think it's trainable also, right?
Yeah, A and B are both trainable.
Yeah, I see. Now it's D by R dimension, so it's much smaller by D by D. Okay.
Yeah.
Okay. Sure.
Yeah. So sorry. Yeah, A and B are both trainable.
Yeah. It's a D by R or R by D. It's much smaller than D squared. Yeah.
Yep.
Okay.
So, any other questions? Nope. Okay, then I will continue going on. So, as I mentioned that from the introduction, that there are a few ways to adapt large language models for downstream tasks, and the two ways that are used will actually be used as baselines in the experiments are adapters and prefix tuning. And again, these have their own problems at the very bottom here. So adapters introduce inference latency, and then prefix tuning is according to, it's difficult to optimize, and also the sequence length is reduced because you have to accommodate for additional input. And the way I understand adapters is that these are added inside the pre-trained transformer. So you have a transformer layer, and then you have this adapter, which is just a model, a model essentially. And in this case, it's just 2 feed-forward layers. And what they do is that you can insert these into inside the transformer layer, in between two parts of transformer layer. For example, here they added between the feed-forward layer and layer norm, and again between feed-forward layer norm again. And you can keep the transformer, the pre-trained weights frozen, and you can fine-tune the adapter layers only. And again, for prefix tuning, the idea here is that you're constructing word embedding models for special tokens, and then those can then be used to condition alongside. They can be used alongside a pre-trained model to condition inputs for a task. So in this case, for example, if you have like summarization, you can have special tokens for summarizing, and then you can have your you can have an article that you want to summarize, and then your model will then summarize it. So then, and again with this, you can have different prefix or different word embedding models for each of the for each task, and those are also relatively small. So that's why they use that there. You don't have to do any kind of tuning for the transformer, the pre-trained models. So I'm going to describe what they mean by inference latency. They did a quick experiment on GPT-2, where they looked at they added adapters to GPT-2, and they looked at the amount of they looked at the amount of time inference took in milliseconds over different batch sizes, and what they saw was that if you were to just do in the case if you have a batch size of 1, if you were to do fine tuning, your latency is about 19.8 milliseconds, and with the adapters it's 23.9, which is about or 25.8, which is a 20 to 30% increase in time. So that's kind of what they mean by why they mention that this introduces inference latency, is that it takes more time to do inference. They do note that as you increase the batch size, that difference does go down. So if you were to use larger batch sizes, I don't think it's as different. But yeah, that's what they mean by inference latency. They show that there is inference latency when using adapter layers. So, and finally, what I'll do is, before we officially go into LoRA, what LoRA is, the paper does provide some explanation as to the issues with fine-tuning large language models. So if you have your conditional language modeling objective, and the idea here is that you want to maximize you want to find a set of fine-tuned weights given your pre-trained weights, and essentially you have this weight change from the pre-trained weights to fine-tuned weights. The problem is that the dimension of the pre-trained weights is the same as the dimension of the weight change. So what that means is, if you were to fine-tune your model, you'd have to essentially be holding that weight change. You essentially have to have that weight change there, which if you're tuning GPT-3, that'd be 175 billion parameters. So the idea here is that what they want to do is they want to take this weight change delta, and they want to decompose that into 2 matrices that are much, much, much smaller. And that's essentially what LoRA does. Does anyone have any questions before I go into what kind of the core part of LoRA?
I think it just looks like a patch. The data is just a patch. I mean,
yeah, it's basically, that's kind of the way I also view it, is that it's more of a if you have some weights that are pre-trained, you can just have the weights alongside this other this additional 2 matrices, and yeah, I can see this. I can see it as a patch, essentially.
yeah, it's a patch. I mean, they are doing a transformation from a bigger dimension to a smaller dimension. So you train 2 matrices of a much smaller dimension, but then you you transform back to the the larger dimension, but but you change smaller matrices and you add together. It's a patch.
Yeah. Yeah, but again, the benefit here is that you don't have to tune any of the pre-trained weights. Those essentially remain frozen and can almost view them as like they're essentially features that you can add to whatever LoRa learns.
Right. I think that's a very clever idea.
Yeah. So yeah, essentially this is where this gets more into the details of what LoRa, like the kind of the matrices that LoRa learns. So so essentially we take that delta in the weights and we break it down into B and A. B here is D by R, and then A is R by D. These are two matrices where R can be substantially lower than B. Like if D is, for example, if we're using GPT-3, I think D would actually be a 418,000 there. So it would be 418,000 by 1 if you were to use a range R equals 1. So these are R can be substantially lower than the original dimensions of the model. And what you do essentially is that whenever you have a set of pre-trained weights you want to add LoRa to, you keep those pre-trained weights static, and then you add this matrix A and B, and then whenever input comes in, you run it through the pre-trained weights. You then run it through B times A. You run first A and then B, and then you concatenate. You add the two together to get your output. So if you were to not use LoRa, you just have only you'd only pass your input through your pre-trained weights and then get your output H. With LoRa, you add these additional trainable weights B and A. So does anyone have any questions about that?
This is just a comment. I think otherwise it's a quadratic, D squared, but now it's becoming linear, because R is very small, 1 or 2, so it becomes linear, that's the reduction, significant.
Yeah. And one thing to mention here, so the A equals N, the normal distribution, that's essentially, these are the initializations. They initialize A to a random Gaussian, and then they initialize B to 0. So at the very start, you get nothing from LoRa, and then as you tune it, you get more and more information from LoRa. So with that, I can then go into kind of the benefits of this. Again, I mentioned that there's no additional inference latency. So the one really cool thing with this is that if you want to switch between different tasks, what you can do is, because it's just WX plus BAX, you can subtract out BA for for one task, and then you can just add BA for a new task. So you can essentially do some basic subtraction and addition for adding weights for different tasks. And again, in this case, the pre-trained weights are just shared across all the tasks there. The other benefit is that, again, it reduces memory and storage use. So if you were to, if I understand correctly from the paper, GPT-3 is about 350 gigs of memory. And if I understand this correctly, it becomes 1.2 terabytes if you fine tune it. But if you were to use LoRa, you'd have the 350 gigs of GPT-3, and your LoRa matrices could be roughly substantially much smaller than that. So you can have about, like, for example, in this case, 35 megs. So instead of having 1.2 terabytes of memory for fine-tuning GPT-3, you can instead use 350 gigs plus 35 megs. for essentially adapting GPT-3. And finally, the other cool thing with LoRA is that if you want to actually get the full fine-tuning back, you can increase the rank R back up to the full dimension of the you can increase the rank back up to the full dimension of the model. So you can get R back to like you can instead set R equal to D, and then you get your full fine tuning back.
What is full fine tuning here?
So meaning if you were to not have LoRA and you were to fine tune a model without if you were to just fine tune the model, so without LoRA in it.
Okay, so but if we increase the rank and we keep both the pre-trained weight and A and B matrices, then with twice the amount of weight, it converges to full fine tuning.
Yeah, I think it may actually be not sure exactly if it's R equals D or E or equals D or D over 2, but essentially as you increase the rank, LoRA will converge. According to the paper, LoRA will converge to just doing fine tuning with the pre-trained weights.
Okay, so the way the performance of the model increases as we increase the rank of R.
I think so. I think yeah, you can see it as that, but yeah, I think in some of their experiments they do mention that they get better performance if they have lower rank. So I'm not sure if the performance will increase, but you recover doing fine tuning without you essentially recover doing fine tuning of the pre-trained weights.
Okay.
Any other questions? Then I will go into the experiments from the paper. For their experiments, they use a few baselines. The first one being just fine tuning. So you take a pre-trained model and you fine tune the model. They do have one variant of that where they specifically for GPT-2, where instead of fine tuning the entire model, they keep everything but the last 2 layers frozen and only adapt the last 2 layers of the model. There's also a bias-only baseline where they keep every other parameters frozen except for the bias vectors, and they only tune the biases. There's also the prefix tuning, and essentially this is again this essentially training a word embedding model for training a word embedding model for special tokens, and then inserting those special tokens into your input. They also did have an extension of that where prefix embedding tuning only really does that at the embedding layer of a model. They also looked at if they were to do that for every layer in your transformer model. So they have that as an additional baseline. And then finally, they have the adapter tuning, and there's a bunch of different variations on the adapters that they have. The 4 adapters here are based on on prior papers, and I won't go into them here in too much detail, but essentially there are 4 different adapters they look at. And then finally, they have LoRA. One of the things that they do here is that they restrict their experiments and their analysis really to the self-attention mechanism of the transformer models. So specifically, they look at, in their experiments, they look at the, so there's, in the self-attention, you have query, key, value, and output matrices. And they specifically focus on adapting the query and the value matrices. So then, with that, we can actually go into some of the experiments. So the authors would run experiments over natural language understanding and generation tasks. We'll begin by looking at some of the understanding tasks first. So for natural language understanding, they use three different models: Roberta Base, Roberta Large, and Roberta XXL. And again, these are each of those models are trained with different training methods that I provided in the previous slide. So you have your fine tuning, your bias only tuning, your adapters, and also LoRA. And they apply these models and the tuning methods to a bunch of different tasks from the GLOOP benchmark. And from their results essentially show, like, at least for natural language understanding, they do have some mixed performance. LoRA sometimes does perform well, but other times other methods perform better than LoRA. So this kind of becomes it gets better when they look at natural language generation, where when for this, what they do is they look at GPT-2 and GPT-3, and specifically this slide here will present GPT-2, and the next slide I'll present GPT-3. And here again, they take GPT-2 and they use the different baseline tuning methods to over GPT-2. And what they see is that, the task data set they use is the E2E NLG challenge, which is the end-to-end natural language generation challenge. And what they see here is that this is where kind of LoRA actually performs much better over the baselines. So here in this case, if you were to look at, I forgot to mention, they use GPT-2 medium and GPT-2 large. So if in the medium case, LoRA outperforms all of the other baselines, and in the large case, it performs the majority of the baselines. So for natural language generation, it looks like LoRA actually performs better compared to natural language understanding. And then finally, they perform again on GPT-3, and this is where they see the highest performance gains. So here, essentially, LoRA actually outperforms outperforms the baselines in this case. So yeah, again, what's interesting is that yeah, for natural language understanding, it doesn't perform well, but for generation, it performs much better. I'm not sure why that's the case, but they didn't really describe in the detail why understanding performed worse in generation, but yeah, it looks like that's the case. And here, sorry, the data sets they use here are WikiSQL. That is, forgot what that is. That's, double check. What is that? I think it's Wikipedia and Wikipedia to SQL, and then MLI, which I actually forgot what that is. And then Samsung is summarization. Does anyone have any questions about this?
So they didn't mention anything more on why it performs better on NLG and not on NLU.
I didn't see anything in the paper. They just mentioned it could be in the appendices. Which I only gave a brief check, but it looks like yeah, I don't think they provided any. Let me just double check.
Yeah, because it's quite interesting, don't you think? Like only on specific kind of task it works better.
Yeah, that surprised me. Yeah, I don't know why that's the case, because like this should be task independent. So it shouldn't be, you should see this similar performance behaviors between understanding and generation, but for some reason generation just performed better.
Yeah. Maybe
So-
because in NLU datasets they have to do a prediction, some sort of a binary prediction. But here they are predicting out of a much larger vocabulary. Would that make sense?
I see. I think so, yeah, perhaps. Are there any other questions? They also do one additional just experiment with GPT-3 where they look at the number of trainable parameters and they look at the effect of these trainable parameters on the validation accuracy for SQL and multi-NLI. And what they noticed was that essentially if you increase the number of trainable parameters, LoRA performs consistently if you increase the number of parameters, but there are other models which actually perform well and then just they drop. Like for example, in this case, prefix embedding has that behavior, and also prefix layer has that behavior. But when you use adapters, it looks like the at least one of the adapters, adapter H, it looks like that doesn't have that behavior, or it's not as pronounced as the other tuning methods. So yeah, that kind of the conclusion that can come out of this is that with LoRA, if you increase the number of trainable parameters, you don't drop in accuracy, but you do remain at the same, at least for validation accuracy, you remain at the same validation accuracy. So with that, so I can stop here or I can continue going forward. The next section is more about studying the subspaces of these the adapted matrices of LoRa trains. So I can continue. I can go through those as well if people are interested.
Yeah, go for it.
Cool. So in that case, what I can do is I will stop sharing this and I will go straight to my to the paper itself. All right. Can you all see the paper?
Yeah, I glanced over it a little bit.
Okay, so basically the this section they look at they want to understand the properties of the learning adaptation matrices that LoRa learns for downstream tasks, and they specifically focus on using GPT-3 because that's where they got they were able to reduce. They had the largest reduction in number of parameters without actually affecting task performance substantially. So there are three questions that they look to answer. The first one is, if I were to give you a budget constraint, which subset of the weight matrices in a pre-trained transformer, specifically within self-attention, should I adopt? And the second one they look at is what's a good rank to use in practice? And then also the third thing they look at is if I were to take these adapted weights that LoRA learns, how does that correlate with the pre-trained weights? So, and the idea here is that if you were to look at 2 and 3, that could actually potentially help shed light on some fundamental principles of using these pre-trained models for downstream tasks. So, which I think is an important topic within NLP. So, first one is, again, which matrices should we use should LoRA adapt, essentially? So what they did was they took a parameter budget of 18 million. This is 35 megabytes if stored on using SP16. And what they do is they look at rank 8, 4, and 2. So this is the R value there. And what they do is they look at the 4 different attention weights that you can adapt. So the query, key, value, and the output. And they look at them separately, and they also look at them in pairs together. So they look at query and key, query and value, and then they also look at all 4 of them together. And what they and specifically, again, given this GPT-3, they apply it to the WikiSQL and multi-NLI data sets. And what they see is that if you were to adapt both query and value, either both of them together or with in conjunction with all the other weights, you get the best performance. So one thing to note here is that given that you have a parameter budget, if you want to adapt more weights, you have to reduce the rank. So the rank does, in this case, you have to use the rank of 4 if you're using 2, and then rank of 2 if you're using all 4 weight, if you're adapting all 4 weights. And what's neat about that is that the best performance does come from at least using 4 and 2, which means that it looks like if you decrease the rank, at least for these 2 data sets, you get better performance. Specifically validation accuracy performance on these 2 data sets. And in the second, for the second question, which looks at what's the optimal rank for LoRA, what they do is they take they vary the rank, so from 1 to 64, and they adapt only the query and values, the query, key, value, and the output, and just the query, and they compare across all 3 of these. And one thing they noticed is that one thing that was surprising is that if they were to use a rank of 1, they actually get pretty good performance. Specifically, if you are, again, if you're adapting the query and the value, you get pretty good performance if you use R equals 1. But if you were to use something much higher, you may also, in WikiSQL, your performance reduces, it looks like, but with multi-NLI, it increases. So does anyone have any questions here? The main conclusion here is that it's possible to achieve pretty decent performance if just using the simple rank of 1. So in other words, A and B are basically vectors.
Multi-NLI is a generative task, right?
Yeah. So these are all generation tasks.
Okay.
So with that, what they do is they take this and they actually do 2 additional experiments. So they take a rank of 8 and 64, and they look at the subspace similarity between these 2 ranks. So what they do is, So if you recall, LoRA has A and B. It trains two matrices A and B. They specifically focus on A here. And the idea here is that the way they do this is they want to do is they want to look at how the subspaces, how much they overlap between the two ranks. And the way they do this is that they take A, they perform singular value decomposition. They get their these singular vectors, and then they use something called Grassmann distance over those singular vectors. And what they do is they vary how many singular vectors they see for each of the ranks. So for rank 8, you have 1 through 8, and then you have for 64, you have 1 through 64 possible singular vectors. And essentially the idea behind the Grassmann distance is that you have if you were to have as you go higher, it means you're overlapping more. And here 1 represents a complete overlap in subspaces, and 0 means a complete separation. And what they see is that at rank 1, so if you were just to use the top singular vector, that already has a pretty decent overlap between 8 and 64. The remaining don't have much of an overlap, but 1 specifically does have a pretty high overlap. So from what they so that essentially can provide an explanation as to why R equals 1 performs quite well, because essentially, from my understanding, you need just a rank. R equals 1 is essentially where you have the most overlap. And let me see. And according to the paper, it looks like the other the other ranks, it looks like they have mostly random noise. So that's where they conclude you can have a very low rank with these adaptation matrices. They also do look at the similarity between, like, if you were to take a single rank and look at the different, if you were to have like 2 separate runs, to see if this, that to see if you still have overlap within the first singular value or singular vector, sorry. And it looks like that they do see this. So what they did was they took 2 random they did 2 runs. They took took the matrices A that they learned that LoRA tuned, and looked at the again the Grassmann distance between the 2. And what they saw is, again, R equals 1 is you have the most overlap in the first singular vector. And for comparison, they provided random Gaussian, which should have 0 overlap. So the final thing they do is they want to look at the correlation between the pre-trained weights and the weights that LoRA learns. And the way they do this is that they take the pre-trained weights and project it into the subspace of different they project it into the different subspaces of these different vectors. So you can either have the ones that LoRA learns. You can either have the pre-trained ones, and you can have a random one. And in this case, if you were to project frozen parameters into a subspace of the frozen parameters, that could have the highest correlation. So, and that's kind of what they see here is that if you were to project the frozen weights into the subspace of what LoRa learns, you actually do get some relationship between the two. And what they did was they essentially concluded that given this, that the low-rank adaptation matrices potentially amplify important features, specific downstream tasks that were learned but not emphasized in pre-training the model. And does anyone have any questions about this? If not, we can just conclude right here. Essentially, some directions for future work could be that you can combine LoRa with different adaptation methods. You can also look at the mechanism behind fine-tuning LoRa. You can also look at the it's unclear what how to choose the weight matrix to actually adapt, and also to finally you can also look at whether or not the actual pre-trained weights are rank deficient as well. So that's essentially the end of the LoRa paper here. If anyone has any questions.
Great. Thanks for the presentation.
Yeah.
So if you want, I can quickly discuss the code. If it's okay, we can discuss it next week also.
You can, if I have some time, so I could definitely stick around for going through the code.
Okay. I will share my screen. So the most important part of this library is here in this file, where they are basically they are defining these LoRa classes, and what they've done is they have defined a base class called LoRa layer, which has the properties that are included for LoRa implementation, like what is the dimension, R dimension, and what is the LoRa alpha. LoRa alpha here is like a constant which they use it for for implementing a scale to reduce the values. There's a LoRa dropout. Basically, the dropout for the matrices involved in the LoRa layer, and these two variables I'm not sure, but I have some thought. I'll discuss that later. So they are used to toggle behavior at train and test time. And merge weights is basically about whether you want to add the changes that LoRa, the updated weights of LoRa, do you want to add it to the matrices? So yeah, I'm still not sure about that. So what they have done is like they have defined different classes, like an embedding class and a linear layer, so that these can be easily included there. So if we talk about this linear class, which involves both LoRa and NL.linear, so here they initialize their linear layer that they had initially, and now with that they will also have a LoRa layer which has the same properties we just discussed now, And now if we want to have any trainable parameters and we know that if the input for that R value is greater than 0, then we define the two matrices LoRa A and LoRa B. And this is the scaling factor where they use LoRa alpha and the dimension that they use for creating these matrices. So yeah. Yeah. So at whenever there's an input X, if the dimension of if the dimension R dimension is greater than 0 and self dot not merged, so self dot merged here is kind of a toggle between, as I understand, Tilmas, between train and test behavior. So this is so first they calculate the result of the linear layer that they have already with the its initial weights and biases, and then they add the result of that with the multiplication of we saw that equation, right, where h of x was equal to w of x plus bax. So it is implementing the same thing here. Yeah, and then they both add this result to this one. And I'm still not sure about why this behavior is like. Is it at runtime, at train time? Is it at train time they are adding the result of the LoRa, whatever the LoRa weights learned to the output of that particular layer, and at test time they are just using the initial weights. So if you see here, they are toggling this variable, this right, self dot merged here. So whenever they set the mode equal to train, what is happening is that if the self dot merge weights, which basically dictates whether you update the weights or not, and it depends on this toggle variable self dot merged. So if we initialize the training with the train mode, what will happen is, and if we have activated LoRa, we will subtract the weight of the weight matrices by this factor here, and we set this value as self dot merged equal to false. So when that input comes to the forward, this thing becomes not false. So at train time, this thing executes, and at test time, this is not executing. And if we toggle the mode from train equal to true to train equal to false, what happens is that since it was last training, this not self dot merged becomes true, and at test time we are adding the weights of adding to the weights with this value. So this is what is happening, and I'm not sure why this is happening. I was hoping that maybe it gets covered in the paper. But Pawan, any idea why they might be doing it at different test time? Like, what is this behavior at train time and test time? Any idea?
See, scrub merge. I am also. So we have. Can you zoom into the? Let's see. I'm also not sure. I know that there's a scaling. I know the scaling is there, but so why make sure the weights are not merged? Merge the weights. Switching train mode. Not merging the weights. I'm actually not sure. Yeah, why they're. Oh wait, hold on. Is weight? Let me see. What is self dot weight?
Self dot weight will be coming from here.
So it's. I am not sure why they do this.
Okay, so I guess what I'll do is I will revisit this repository once more after reading the paper again.
Okay.
yeah, maybe I get some idea. Then I can cover this next week with when we talk about the code about PEFT.
Okay. Yeah, I'm not sure. If it's training.
Yeah, because this behavior, right, is present for other layers also. So this is some sort of a toggle behavior at the train and test time. So I'm not sure why this is happening. But yeah, other than that, the forward layer. So here is a similar thing for an embedding layer. So what happens here is that again they define the same parameters LoRa A and LoRa B, and what happens is that at training time, whatever their initial output is there from the embedding layer, they add the output from LoRa to the result there. And yeah, so the code implementation is fairly straightforward in the way that they have an additional parameter, and during the forward pass, those parameters add to the value of the final result. There is some strange behavior around test time and train time, which I will check
Is
once again.
weights all of the weights, including the pre-trained model?
No, it will be only for this layer. So, so the cell dot weight will be coming from here.
Okay. Gotcha.
Yeah, I guess I'll revisit this once more and I'll get back to it tomorrow, next week.
Gotcha. Yeah, I can. Let me know if I can help in any way.
Sure. Yeah. So I guess that's it for today's meeting, guys. Thanks again, Pawan. Great presentation. Really interesting paper. Kind of shocking how it is able to do it. Yeah.
Yeah.
I think quite an interesting idea.
Yeah.
Cool. Any other questions? I think that was, yeah. Thanks again.
I saw a paper by Jeffrey Hinton and maybe his colleagues about forward gradient thing. They're trying to find an alternative for back propagation. Wow. I don't know whether that will be successful, but if it's successful, that will be a revolution.
Are you talking about the forward? I think there's a FF or something. Paper.
They do the calculation of a gradient in the forward pass, not in the the back propagation. I did not read the paper. I only read the title. I mean, the paper was published like a few months ago. I saw it today. I mean, I don't know whether that's something interesting because I don't know whether it will be successful. But here is the paper. Let me set the link to the.
Yeah, we were about to cover that paper, but we didn't. I was about to prepare, but it was quite tough.
But besides that, good presentation. It's a clever idea for the paper is really a clever idea. Yeah, for this one.
Yeah, I'm still a little baffled by the difference between understanding and generation. Like that's still a little bit surprising to me.
What I was thinking was like usually when we used to think about adding parameters to the model to make it learn a new task. We usually used to think about adding the parameters at the top, right? And maybe in a linear session of like what adapters are doing, right? And in a sequential process, you add a new component. This LoRa paper is adding it in parallel instead of adding it sequentially either on top or bottom.
Yeah, I know the of like for a while, like years ago, it used to be that you add layers at the top, and I think even
Yeah.
the adapters are sequentially with the pre-trained weights, but this
Yes.
one is in parallel.
Yeah. And that somehow makes it better at generation.
Yeah.
That's interesting.